Hello, good day, all of you. Today we will discuss basic satellite communication part 6, which we will continue for link and link analysis. Last session we have talked the link analysis, some major parameters. There, carrier to noise ratio at the receiving station has to be measured or to be assessed. In satellite communication, basically in geosynchronous or geostationary satellite communication, we will have satellite in geo-equatorial orbit, and it will have minimum where 90-degree elevation will be there, that is 35,786 kilometer, and maximum it can go in 0-degree elevation point around 42,000 kilometer, and this difference will be minimum, and the distance in dB it will be around 1.4 dB. That's why it is called distance insensitive communications. And we'll have two link because the satellite will work as a bent pipe for the frequency translation. It will receive the transmit frequency and it will transfer to downlink frequency and channelize, amplifier, and again retransmit through it antenna. Therefore, it will have one is uplink and other is downlink, and uplink will be generally for better ERP, hence we will get C by uplink is more compared to C by N downlink in other side receive station, because here the satellite ERP will be restricted as per the satellite TWTA and antenna size. Some point also uplink will be weak compared to downlink, that is where called a multi-point to point communication or like that. But here anyway we will see it does not matter, because the overall at the receive point, the overall C by N naught received is the effective C by N naught, that is both uplink and downlink C by naught will be contributed. That's why this is C by N uplink will be transmit power plus transmit gain, which will be equivalent isotopic radiated power, then minus that path loss and minus Boltzmann constant, and plus G by T, which is one figure which will be derived from the receive station or receive antenna of satellite, and this is called the figure of merit of the earth or spacecraft terminal, then minus the other losses like atmospheric losses and polarization losses, pointing losses, and rain losses. Therefore, for uplink in will be ERP of Earth station and G by T of spacecraft, and for downlink ERP of spacecraft and G by T of Earth station. Here the uplink ERP will be maximum compared to G by T of the spacecraft. But here in downlink ERP and G by T will be, if bigger antenna, then G by T will be more, and smaller antenna G by T will be less. Therefore, here the spacecraft ERP compared to Earth station ERP will be minimum, and here the spacecraft GYT compared to the earth station GYT also minimum, because here in satellite the antenna will look towards the cold sky, and here antenna will look to the ground. Sorry, the spacecraft antenna will look to the ground, which is hot, and it will give 290 Kelvin. But in ground station antenna will look towards the sky and will have the minimum temperature. That's why in ground station we will have, because satellite ERP will be limited, then we will have maximum GYT. That means G will be maximum and T also minimum. And it is design or consideration that how to make the T system of the ground receive terminal is minimum to minimum to achieve better C by N naught. And the losses, the atmospheric losses, which will be the oxygen evaporation will interact to the electromagnetic waves, and that will have some loss, and that loss will depend upon the band of frequency. That is in a C band, say 4 to 6 gigahertz, it will be 0.04 dB divided by sine elevation angle, because when sine 90 it will be same dB, but when elevation will be less and less, this figure will be more, then it will be 0.04 divided by sine elevation, and for Q band it will be 0.11 divided by sine elevation, and Ka band 0.25 dB divided by sine elevation. Next is pointing loss, because the earth station antenna and the spacecraft antenna should be pointed and to be each other in a correct direction. If something will be disturbed, the antenna position will be disturbed, the reflector will be not aligned properly, then we will not have the proper communication. The signal will be lost. Therefore, the pointing loss, it depends the half power beam of the antenna, and here because this satellite antenna beam width will be maximum to cover the footprint of the earth, but ground station antenna has to only point at the satellite. That's why this half power beam width will be very minimum, and it depends upon the frequency of operation and size of the antenna. That is theta 3 half power beam width will be 70 lambda by d diameter, or it can be calculated as 21 divided by f in gigahertz and d in meter. Then the loss will be 12 into offset from the main beam divided by the theta 3 dB, half power beam width, square, and it will be calculated as dB. Then when antenna size will be more and the beam width will be lesser and lesser, this figure will be increased. And similarly, polarization loss, actually the communication will be established by matched polarization, that is either CP circular polarization or LP in linear polarization. LP also two ways will be there, one is vertical and one horizontal polarization. If transmit will be horizontal, then receive and both sides will receive horizontal. Similarly, if downlink will be vertical, that means generally we will opt, say this communication will take place in C band. In C band, uplink will be 6 gigahertz and downlink will be 4 gigahertz. If 6 gigahertz will be horizontal, then both satellite receive and ground station trans will be horizontal polarization, and downlink will be 4 gigahertz and that will be vertical polarization. Because the polarization and frequency both are difference, and there will be no oscillation will take place either in ground station trans receive side or the satellite trans receive side. Therefore, in polarization loss, in generally it will be 0. But some cases like very lower band of operation like telemetry, tracking, commanding, this type of operation, satellite will have circular polarization, and it will have another benefit also. For linear polarization has not to be optimized by physically movement of the antenna. That's why that mismatch polarization will be used. Either CP, one side, trans side is CP, then receive side will be LP, or vice versa. In that way, LP to CP 3 dB loss will be encountered. That for LP to CP. Otherwise, if in circular polarization also left hand or right hand, there will be no mismatch loss. It will be same polarization. The communication will take place. Then for this only 3 dB will be encountered. Then 4 is rain attenuation. Rain attenuation will happen generally above 10 gigahertz because in higher frequency K band and onwards, the lambda will be less and less. It will be in a centimeter or a millimeter size, and that will interact with rain rate. Therefore, it will be rain rate will be L into alpha R rain rate and beta. This alpha and beta are the constant, depends upon the frequency of use and some extent of polarization, and L is called equivalent path length, and this L depends upon the latitude of the earth station and elevation angle of the earth station, and this alpha R to the power of beta is called specific attenuation. Therefore, in that way, the attenuation are calculated, and for the area, for the receive or transmitting station place, geographical place, and the rain probability, this will be calculated. Then when we will transmit, we will calculate C by N uplink, and in downlink we will calculate C by N downlink. Then, but generally both will as a combined parameters will get the effect for processing the information. The combined C by N downlink is equal to ERP spacecraft minus path loss minus Boltzmann constant plus G by T of station and miscellaneous loss. And this total C by N total is equal to C by N naught uplink and C by N naught downlink divided by C by N naught uplink plus C by N naught downlink. In logarithm, generally what we discussed in communication, always we will talk about ratio, but we will answer or calculate everything is dB, which will be very simplified way. Then it will be minus 10 log 10 to the minus C by naught uplink divided by 10 and C by plus 10 to the power of minus C by naught downlink in dB divided by 10. Then finally we will talk about C by N with some bandwidth, or digitally we will talk about EB by N naught. EB by N naught, energy per bit divided by noise density. That will be C by N naught total, whatever effective C by N will achieve, C by N naught total minus 10 log information rate, RB, where RB is equal to information rate in bits per seconds. Then this EB by N naught and C by N naught formula will be C by N naught minus 10 log RB is equal to EB by N naught, or C by N naught minus EB by N naught is equal to 10 log RB. In that way, we will go one link budget example, the figure wise. Then we can analyze that and how it will be used for communication purpose and designing the link. Very simple way. Excuse me. This is a small example. You see the parameters are what we discussed. It is ERP, G by T, and the measure parameters is C by N, not effective. Then we will have uplink, which will be ground to satellite, then downlink, which will be satellite to ground. In uplink, the ground station will be transmit, satellite antenna will receive. In downlink, satellite antenna will transmit and ground receive terminal will receive the carrier. Then the say will start the high power amplifier, which is the power amplifier will amplify the information and it will be amplified. Generally in amplifier stage, high power amplifier, traveling wave tube amplifiers are used maximum. SSP also used. Then high Klystons are used. Here for 450 watt, the ground station is using TWTA and that will be 10 log 450 watt is equal to 26.53 dB double. And waveguide loss will be HPA to antenna feed will be 1.53 dB. And antenna gain, say we consider 7.2 meter trans antenna and ground station, 65% efficiency at C band frequency 6.23 GHz, which will be 51.56 dBi. That is formula and 4 pi A by lambda square, or in logarithm 20.4 plus 10 log efficiency 10 log 0.65 plus 20 log bracket F in gigahertz and D in meter, then it will find this 51.56 dBi. And if the power and the gain will add in dB, it will be ERP dB double. Equivalent isotopic radiated power 76.57 dB double, and path loss for this, say the distance will be 36,582 kilometer for that, and frequency will be 6230 megahertz. Then by this formula, path loss will be 32.45 plus 20 log f gigahertz plus 20 log r kilometer will be 199.6 dB. This is path loss. Then what in it is a C band. We will talk only atmospheric loss and the pointing loss, and that too will be atmospheric loss 0.1 and 0.55 is pointing loss. Total will be 0.6 dB loss. Then receive antenna gain at satellite, that is 0.7 meter diameter of satellite receive terminal, and that is 50% efficiency. And the gain will be accordingly 30.18, and antenna looking towards the ground station, that will look 290 degree Kelvin, the antenna temperature, and 400 Kelvin is LNA temperature. Total will be 690 Kelvin, which will be 28.39 dBk is a T system. Then G by 2 will be G minus T is equal to 1.79 dB bar K. And Boltzmann constant, which will be 1.38 into 10 power 9, 10 to the power of minus 23 joules per Kelvin per hour will be 10 log that 228.6 minus 228.6. If we calculate, if we put in this formula, ERP minus path loss minus extra loss plus G by T minus to minus plus K will be 106.82 dB hertz in C by N uplink. Similarly, the downlink from satellite to ground station, satellite will have a 0.7 meter antenna and will have a TWT 32 watt, it will be 15 dB double. Satellite 7.7 meter dia, 50% efficiency at 4005 megahertz. It is 6 gigahertz uplink. Here 4 gigahertz downlink. Then the gain will be 26.35 dB and satellite ERP will be 40 dB double. And here waveguide loss 1.35. Then 15 minus this plus the 40 dB double. And the loss will be atmosphere is 0.1 and pointing loss will be 0.25. Because here higher antenna, here there are 0.55. Here lower dia antenna 3.8 meter. That's why here this is assume 0.35 dB. And ground receive 3.8 meter dia antenna 65 efficiency gain will be 42.18. T system, here the LNA will be only 30 Kelvin and antenna is looking to the cold sky which will be 55 Kelvin, which is equal to 85 Kelvin. 10 log 85 will be 19.29 and G minus T is equal to 22.9 dB per Kelvin, which will be G by T. Then Boltzmann constant same, and here the C by N naught downlink will be calculated similarly. ERP and not path loss, excuse me, here I lost, it will be path loss 195 point 195.83 195.83 and the here we have taken 37,000 kilometers distance. D is equal to 37,000 kilometer. Therefore here 195.83 and loss will be 0.35 dB and here ground station antenna 42.18 G and T will be 19.23, G by T 22.9. That's why ERP minus path loss minus extra loss plus G by T 20.9 minus to minus plus K, then is equal to, we will get 95.32 dB hertz, which will be C by N downlink. Then C by N total, which will be effective, similar way if we will calculate, it will become 95.02 dB hertz. Always it will be say it is uplink is 106, downlink is 95, then it will be lesser, just lesser than 95.02 will be there. This is our effective C by N naught. Now let us see with whatever availability is there, we got this much C by N naught carrier to noise density. Now we will see how much information we can transfer with this link. EB by N naught for any processing demodulator, say 10 to the power of minus 6 bit error rate, EB by N naught is required 11 dB. And always we have to keep some margin. Let us, it is a C band, we will keep it a only 3 dB margin here because rain will not have much impact. But the 3 dB will some any equipment degradation or atmospheric some disturbance, we will keep it at 3 dB margin. Then we want EB by N naught 14 dB for processing the information. If we want 14 dB EB by N naught and we have achieved 95.02 dB hertz, then how much information we can transmit? That is 10 log information is equal to C by N naught total minus EB by N naught. required EB band this much, achieved CYN total this much, and then find out the information rate will be say 81 dB beats per second. 95 minus 14 is equal to 81 dB beats per second, which will be in anti-log RB will be 125.9 megabits per second. Then here this much we can transmit. Similarly, if we will go other way, say some requirement is there, our information we have to pass from the transmit station to the receiving station, and the satellite manufacturer, he has given his transponder specification how much it will receive. That means what the satellite receive terminal G by T and what will be the transmit terminal of satellite the ERP. Then to know this information rate, we will cross calculate and we will come out what is the transmit terminal ERP is required and receive terminal GYT is required. Then after knowing all those things, we can choose the what kind of station is required, how much diameter antenna is required, what is the power size is required, and receive also how much antenna dia is required and terminal is the LNA noise dampers are required. And now any single station will have both uplink and downlink. Here the satellite terminal will transmit a portion of whatever requirement in a band, but receive, it will receive all entire things from the satellite, but it will choose what is required by filtering or by tuning its own local oscillator in the down counter section. Therefore, the terminal to design in such a way, it will give uplink requirement and downlink requirement. Though it is not necessary to receive its own downlink, but it will receive from the other side parameters what other station will transmit to this point. Therefore, some mostly all standard size antenna or some link, always the terminals are better in a transmit and a receive side, and some occasionally some terminals like a DTH, those are in one side, only receive terminals are there, but VSATs are in both way, trans and receive. Similarly, this antenna has to be designed. And next, I hope the link budget, very simplest way we have put it here, and in when times come, we will revisit this link budget from one side to other side, like VSAT link budget or some mobile terminal link budget like that. And next part we will go for our station technology, the ground station technology. I hope we will close for this in this point, and thanks a lot for watching.